Welcome, everyone. I'm excited to kick off today's presentation. The topic is equilibriums. We'll be exploring how different systems reach balance, what influences these states, and why they matter. Over the next few slides, I'll guide you through key concepts, examples, and applications. Let's get started. Let's start by understanding what equilibrium is all about. At its core, equilibrium is a state where the forward and reverse reactions occur at the same rate, resulting in no net change in concentrations. This concept is fundamental across many chemical processes. Moving on, we explore how these equilibria can be depicted visually, helping us grasp the dynamic balance that exists. The equilibrium constant, often denoted as K, quantifies this balance. It tells us whether products or reactants dominate under certain conditions. Next, we look into the general law of chemical equilibrium, which relates the concentrations of reactants and products at equilibrium to this constant. It's a key tool for predicting the behavior of reactions. We then delve into the specifics of physical processes, such as solubility and phase changes, and how they reach equilibrium. Understanding these helps explain phenomena like dissolving solids or gases in liquids. In addition, we examine how to predict the extent of a reaction, whether it goes nearly to completion or stops early, based on the equilibrium constant. Further, we cover homogeneous equilibria, where all species are in the same phase, and contrast that with heterogeneous systems involving different phases. We also introduce the concept of dynamic equilibrium, emphasizing that even though reactions appear static, they are actually ongoing at the molecular level. Lastly, we learn how to depict these equilibria clearly, whether through equations or diagrams, making complex processes easier to visualize and understand. All these points build a comprehensive foundation for understanding chemical equilibrium and its vital role in chemistry. When a liquid evaporates inside a closed container, what's really happening is that molecules with higher kinetic energy are the ones escaping the liquid surface and entering the vapor phase. These molecules are moving fast enough to break free from the liquid. Once they're in the vapor phase, they don't just leave forever. They actually collide back with the liquid surface. Some of these molecules are retained in the liquid, while others escape again. This process creates a sort of balance, which we call vapor pressure. The key thing to remember here is that at this point, the number of molecules leaving the liquid equals the number returning from the vapor phase. When this balance is achieved, we say the system has reached an equilibrium state. This equilibrium is crucial because it explains why vapor pressure remains constant under stable conditions. It's a dynamic balance. Molecules are constantly moving back and forth, but the overall pressure stays steady because the rates of evaporation and condensation are equal. This concept ties into the overall theme of understanding how liquids and gases behave under different conditions. The mixture of reactants and products is called an equilibrium mixture. When a chemical reaction reaches a state where the forward and reverse reactions happen at the same rate, this mixture stabilizes. At this point, the concentrations of reactants and products remain constant over time. It's important to understand that even though reactions are still occurring, there's no overall change in the amounts of each substance. This balance is what we refer to as equilibrium. Recognizing this concept is crucial because it helps us predict how reactions behave under different conditions, which ties into the broader theme of understanding reaction dynamics and control. Now, let's talk about the stage where there is no change in the concentrations. This is called a dynamic equilibrium. At this point, the forward and reverse reactions are happening at the same rate, so the concentrations of reactants and products stay constant. It's important to remember that even though it looks like nothing is changing, the reactions are still ongoing. This balance is what we refer to as a dynamic equilibrium. It's a key concept because it helps us understand how reactions behave in closed systems, and it ties into the overall theme of how chemical reactions reach stability over time. Today, we're diving into the concept of ionic equilibrium. Equilibriums involving ions are called ionic equilibrium, and this is a fundamental idea in understanding how ions behave in solutions. when ions are present in a solution, and their reactions reach a state where the forward and reverse reactions occur at the same rate, we say that the system is in equilibrium. This balance is what we refer to as ionic equilibrium. Understanding ionic equilibrium helps us grasp how solutions maintain a stable concentration of ions, which is crucial for many chemical processes. It's important because it connects to the broader theme of how chemical systems reach stability. So, in essence, whenever ions are involved in a reversible reaction and the system stabilizes, we have an ionic equilibrium. Recognizing this allows us to analyze and predict the behavior of solutions in various chemical contexts. Now let's take a closer look at some classic examples of physical equilibrium. On this slide, you'll see three main types. First, we have the solid-liquid equilibrium, which occurs during melting and freezing processes. Then, there's the liquid-gas equilibrium, like boiling and condensation. Finally, the solid-gas equilibrium, which is involved in sublimation, where a solid turns directly into a gas or vice versa. These examples are fundamental because they illustrate how different phases coexist and balance each other under specific conditions. Understanding these equilibria helps us grasp how materials change states in a controlled manner, which is crucial in many industrial and natural processes. So, recognizing these phase transitions is key to mastering the concept of physical equilibrium in thermodynamics. As a system approaches equilibrium, you'll notice that both the forward and reverse reactions are happening simultaneously. It's important to understand that even at this stage, reactions haven't stopped. They are still occurring. However, what makes equilibrium special is that the rates of these two reactions become equal. So, at equilibrium, the forward reaction is proceeding at exactly the same rate as the reverse reaction. This balance means the concentrations of reactants and products remain constant over time, which is a key concept in understanding how chemical systems stabilize. Recognizing this balance helps us see how dynamic processes can lead to a stable state, connecting directly to the broader idea of how reactions reach and maintain equilibrium in chemical systems. Here, NO2 and N2O4 have reached equilibrium. Once equilibrium is achieved, the amount of each reactant and product remains constant. This means that the forward and reverse reactions are happening at the same rate, so the concentrations stay steady over time. It's important to understand that even though the reactions are still occurring, their overall amounts don't change. This state of balance is what we call equilibrium, and it plays a crucial role in understanding how chemical reactions behave in real-world systems. Recognizing this helps us predict how reactions will respond to changes in conditions, which ties back to the larger theme of controlling and understanding chemical processes. Let's take a closer look at this equilibrium between N2O4 and NO2 gases. When we write the equation with the double arrow, it indicates that both the forward and reverse reactions are happening simultaneously. In other words, N2O4 is breaking down into NO2, while at the same time, NO2 is recombining to form N2O4. An important point here is that, at equilibrium, the partial pressures of these gases are equal in magnitude, which means the rate of the forward reaction equals the rate of the reverse reaction. This balance is what maintains the system in a steady state. This depiction helps us visualize how chemical systems reach a dynamic balance, which is a core concept in understanding chemical equilibria. Recognizing that both reactions are ongoing, yet balanced, is key to grasping how reactions behave in real-world scenarios. And also, the rate of dissolution of sugar is equal to the rate of crystallization of sugar. This means that as sugar dissolves into the solution, an equal amount of sugar crystals form from the solution. The ratio of radioactive molecules to non-radioactive molecules in the solution increases until it reaches a constant value, which indicates that the system has reached equilibrium. When solids are in liquids, and no more solute can dissolve in the solution, we call this a saturated solution. In simple terms, it's when the solution has dissolved as much solute as it possibly can. For example, sugar in water reaches a point where no more sugar can dissolve, and any additional sugar just stays at the bottom. This concept is crucial because it shows how dissolution and crystallization balance each other out, maintaining a steady state. Understanding these equilibrium processes helps us grasp how solids and gases behave in liquids under different conditions, which is fundamental in many chemical applications and industrial processes. When we talk about gases dissolving in liquids, the key idea is that the concentration of the gas in the liquid is directly proportional to the pressure of the gas above the liquid. So, if you increase the pressure, more gas will dissolve, and if you decrease the pressure, less dissolves. Now, when it comes to vapor and liquid equilibrium, the vapor pressure stays constant at a given temperature. This means that at a specific temperature, the rate of molecules leaving the liquid equals the rate returning, so the vapor pressure doesn't change. Similarly, for solids dissolving in liquids, the solubility remains constant at a specific temperature. Think of sugar dissolving in water. At a certain temperature, the maximum amount that can dissolve doesn't change unless you alter the temperature. When we consider solid-liquid equilibrium, there's a unique melting point at 1 atmosphere pressure, or about 1.013 bar. At this temperature, solid and liquid coexist in equilibrium, and if there's no heat exchange with the surroundings, the amounts of each phase stay constant. Now, a really important concept here is Henry's law. It states that the amount of a gas dissolved in a solvent at a given temperature is proportional to the pressure of that gas above the liquid. So, if you increase the pressure, more gas dissolves. If you decrease it, less dissolves. And an interesting point is that increasing temperature actually decreases the amount of gas dissolved, because higher temperatures tend to make gases less soluble. For example, consider carbon dioxide. It exists as a gas in the atmosphere, but it can also be dissolved in liquids like soda. The equilibrium between CO2 molecules in the gaseous state and in solution illustrates this balance perfectly. So, in summary, gases in liquids tend to reach an equilibrium driven by pressure and temperature, which directly influences how much gas can dissolve, as described by Henry's law. This is fundamental in many fields, from industrial processes to biological systems. Equilibrium is only possible in a closed system at a given temperature. That's because in such a system, both opposing processes happen simultaneously at the same rate. When this balance is achieved, we call it a dynamic but stable condition. Now, when a physical process reaches equilibrium, one of its key features is that a certain parameter remains constant at that specific temperature. Think of it like a steady state. The number might stay the same, but the processes are still happening behind the scenes. The magnitude of these quantities at any point actually tells us how far the process has gone before reaching equilibrium. So, if the value is changing a lot, it means the system is still progressing towards equilibrium. If it's stable, then the process has essentially settled into that balanced state. Understanding these characteristics helps us see how physical processes behave in real systems, and it connects to the bigger picture of how systems respond and stabilize under different conditions. As time passes, you'll notice that products C and D begin to accumulate, while reactants A and B start to get used up. This change causes the forward reaction to slow down because there are fewer reactants available, and at the same time, the reverse reaction speeds up as more products are formed. Eventually, these two processes balance each other out, and the rates become equal. When that happens, the system reaches what's called a state of equilibrium. In this state, even though reactions are still occurring, there's no overall change in the concentrations of reactants and products. This concept is fundamental because it shows us how reactions can settle into a stable balance, which is key to understanding many chemical processes we encounter in real life. Let's look at the equilibrium constant for the reverse reaction. It's actually the inverse of the forward reaction's equilibrium constant. So, if we know one, we can easily find the other by taking its reciprocal. Now, when we write the equilibrium constant for a general reaction, it looks like this. A plus B. Shifting to C plus D. The key idea here is that, at a given temperature, the ratio of the concentrations of products to reactants remains constant once equilibrium is established. This ratio is calculated by taking the concentration of each product or reactant, raising it to the power of its stoichiometric coefficient, and then multiplying all the products together, dividing by the same for the reactants. This constant value is what we call the law of chemical equilibrium. The term Kc is used to denote this equilibrium constant, and the expression on the right side, the ratio we just described, is known as the equilibrium constant expression. Because the reactants and products are balanced in the chemical equation, we can relate their concentrations through this equilibrium expression, which helps us understand how the reaction behaves under different conditions. Remember, for any reversible reaction like a plus B shifting to C plus D, this equilibrium constant gives us a quantitative way to predict the direction and extent of the reaction at a specific temperature. This is fundamental because it connects the microscopic concentrations to the macroscopic observable properties, tying into the overall theme of understanding chemical reactions and their equilibrium states. If the reverse reaction takes place, then the first reaction we discussed actually dominates. In other words, the side that was initially favored will continue to be favored in the equilibrium state. Now, when we look at the value of K, especially when K is much greater than 1, it tells us something important. The reaction is product favored. This means that at equilibrium, the concentration of products is much higher than that of the reactants. So, in simple terms, a large K value indicates that the reaction strongly favors the formation of products. Understanding what the value of K means helps us predict the direction in which a reaction will go and how far it will proceed before reaching equilibrium. This concept ties into the overall theme of how we can control and predict chemical reactions based on their equilibrium constants. Let's take a closer look at the range of equilibrium constants. When K is much less than 1, it indicates that the reaction is reactant favored. This means that at equilibrium, reactants are the predominant species. On the other hand, if K is much greater than 1, the reaction is product favored, and you'll find that products dominate at equilibrium. Understanding these key points helps us interpret the behavior of chemical reactions. It connects directly to the overall theme of how equilibrium constants tell us about the position of equilibrium and the relative amounts of reactants and products present. In a homogeneous system, the reactants and the products are all in the same phase, which in this case is the solution phase. This means that everything involved in the reaction, both the starting materials and the resulting products, are dissolved in the same substance. One key point to understand here is that because they share the same phase, the ions involved in the reaction are in equal concentrations on both sides of the equilibrium at the same time. This equality of ions across the reaction helps us understand how the system maintains balance. So, in the next reaction we look at, the ions are essentially in a state of equilibrium, meaning their concentrations remain constant over time. This concept of homogeneous equilibria is fundamental because it simplifies the analysis of reactions where everything is in the same phase, allowing us to focus on the interactions of ions without worrying about phase boundaries. It ties into the overall theme of understanding how reactions reach and maintain equilibrium in different systems. So we know that here, P represents the pressure in pascals, N is the number of moles, and the volume is measured in cubic meters. And of course, T stands for the temperature in Kelvin. Now, if we look at concentration, C, which is in mol per liter, and pressure, P, in bar, then the ideal gas constant, R, is 0.0831 bar liter per mol Kelvin. Moving on to the next point, which is the equilibrium constant in gaseous systems. This is a crucial concept because it helps us understand how gases behave when they reach equilibrium. The key idea here is that the equilibrium constant relates the concentrations or partial pressures of gases at equilibrium, and it's essential for predicting the direction of reactions and the extent to which they proceed. By understanding these relationships, we can better grasp how gases interact in different conditions, which ties back to the overall theme of chemical equilibrium and reaction dynamics. So this slide emphasizes the importance of the parameters involved and their units, which are fundamental for calculating and understanding equilibrium in gaseous systems. Now, let's talk about equilibrium in systems that have more than one phase. We call this a heterogeneous equilibrium. Essentially, this is when different phases, like liquid and vapor, are in a state where their concentrations remain constant over time. A classic example is the equilibrium between water vapor and liquid water inside a closed container. Here, water molecules are continuously evaporating and condensing, but the overall amount of vapor and liquid stays steady. Recognizing this type of equilibrium is important because it helps us understand how different phases interact and coexist in a balanced state within the same system. This concept ties into the broader theme of how equilibria can occur in various forms, whether in single-phase or multi-phase systems. Let's talk about the expression for the equilibrium constant. It's important to remember that this expression is only valid when the concentrations of reactants and products have reached a constant value. That's the equilibrium state. At that point, the concentrations don't change anymore. Another key point is that the value of the equilibrium constant doesn't depend on how we initially started the reaction. Whether we began with a lot of reactants or mostly products, the equilibrium constant remains the same, as long as the temperature stays constant. Speaking of temperature, the equilibrium constant is temperature dependent. It has a unique value for a specific reaction at a given temperature, which means if we change the temperature, the equilibrium constant changes too. And finally, if we look at the reverse of a reaction, the equilibrium constant for that reverse reaction is simply the inverse of the forward reaction's constant. This relationship helps us understand how equilibrium constants relate to each other in interconnected reactions. When A is very small, it means that the reaction doesn't happen very often, so it proceeds rarely. On the other hand, if Kc is very large, the reaction tends to go almost all the way to completion. The key idea here is that the magnitude of these equilibrium constants, whether it's Kc or Kp, directly relates to the concentrations of the products. As these constants increase, the concentration of products increases as well. Conversely, the constants are inversely proportional to the concentrations of the reactants. So, understanding these relationships helps us predict how far a reaction will go under certain conditions, which is a crucial part of controlling and optimizing chemical processes. This ties back to the overall theme of predicting the extent of reactions and managing equilibrium effectively. When Qc equals Kc, that means no net reaction is occurring at that moment. It's like the system has reached a state of balance and nothing is changing in the overall composition. Now, if Qc is less than Kc, the reaction will shift from right to left. In other words, it favors the formation of reactants, moving in reverse. Conversely, if Qc is greater than Kc, the reaction proceeds from left to right, favoring the formation of products. And of course, when Qc equals Kc, the mixture has indeed attained equilibrium. It's important to remember that these relationships help us predict how a reaction will behave at any point. If Qc is less than Kc, the reaction will go forward, producing more products. If Qc is greater than Kc, it will reverse, producing more reactants. This is where the equilibrium constant really helps us. It provides a benchmark to predict the reaction's direction based on the current concentrations. To do that, we calculate the reaction quotient, Q, specifically the molar concentrations denoted as Qc. This allows us to understand and anticipate how the reaction will proceed at any given stage in the process. Let's talk about equilibrium concentration. When a reaction reaches equilibrium, the concentrations of reactants and products change until they stabilize. To find the equilibrium concentrations, we start by substituting the equilibrium values into the equilibrium expression. From there, we solve for x, which often involves solving a quadratic equation. It's important to choose the solution that makes chemical sense, usually the one that results in positive concentrations. Once we have the value of x, we can calculate the actual equilibrium concentrations by relating x back to the initial concentrations. To ensure our calculations are accurate, We always check by plugging these equilibrium concentrations back into the equilibrium equation. Now, before diving into the calculations, we need to write out the balanced chemical equation for the reaction. Underneath that, we'll set up an ICE table. This stands for Initial, Change, Equilibrium, to organize our data clearly. This structured approach helps us track how concentrations change as the reaction progresses toward equilibrium. In this section, our goal is to understand how to determine those equilibrium concentrations systematically. Remember, mastering this process is key to analyzing chemical systems accurately, which ties into our overall theme of understanding reaction dynamics. Let's break down what happens when the standard Gibbs free energy change, G degrees, is greater than 0. In that case, if we look at the ratio G degrees over RT, it becomes negative, which means it's less than 1. Now, remember that this ratio relates directly to the equilibrium constant, K. So, if this ratio is less than 1, then K must also be less than 1. This indicates that the reaction is non-spontaneous under standard conditions, or in other words, it favors the reactants. The reaction proceeds in the forward direction, but only to a very small extent, producing just a tiny amount of products. On the flip side, if G degrees is less than 0, then G degrees over RT becomes positive and greater than 1. That makes K greater than 1, which tells us that the reaction is spontaneous. It proceeds forward extensively, with products becoming the predominant species at equilibrium. Now, taking the antilog of both sides helps us connect these ideas mathematically. When the reaction reaches equilibrium, G equals 0, and the reaction quotient Q equals the equilibrium constant Kc. This gives us a neat relationship. If G is negative, the reaction is spontaneous and goes forward. If G is positive, it's non-spontaneous, and the reverse reaction will tend to occur because its G is negative. And if G equals 0, we've hit equilibrium, meaning there's no more free energy available to drive the reaction any further. This balance point is crucial in understanding how reactions behave and how they shift toward equilibrium. Le Chatelier's principle states that if you change any of the factors that influence a system at equilibrium, the system will respond in a way that counteracts that change. In other words, if you add or remove something, or change the temperature or pressure, the system shifts to restore balance. It's a fundamental concept because it helps us predict how a chemical system will react when conditions are altered. This principle is especially useful when we're trying to control reactions in industrial processes or understand natural biochemical systems. So, understanding these factors and how they interact with equilibrium helps us grasp how systems strive for stability even when conditions change. Le Chatelier's principle predicts that when we add or remove reactants or products from a reaction at equilibrium, the system responds in a way that counteracts that change. If we add a reactant or product, the net reaction will shift in the direction that consumes the added substance. Conversely, if we remove a reactant or product, the reaction will shift in the direction that replenishes what was taken away. In simple terms, whenever there's a change in concentration, the equilibrium adjusts itself to minimize that change. So, if you increase the concentration of something, the system will try to use it up. If you decrease it, the system will produce more to replace what's missing. This is a key concept because it shows how dynamic equilibrium truly is, always responding to keep things balanced. Understanding this helps us predict how systems will shift when conditions change, which is essential for controlling reactions in both industrial and laboratory settings. Let's talk about how temperature generally affects reactions, especially in relation to the enthalpy change, or H. When a reaction is exothermic, meaning it releases heat and has a negative H, increasing the temperature actually causes the equilibrium constant to decrease. So, in this case, raising the temperature shifts the equilibrium to the left, favoring the reactants, and results in a lower concentration of products. On the other hand, for endothermic reactions where H is positive, increasing the temperature has the opposite effect. It causes the equilibrium constant to increase, shifting the equilibrium to the right and producing more products. This concept is crucial because it highlights how temperature adjustments can control the direction and extent of a reaction. Remember, raising the temperature generally shifts the equilibrium to the left for exothermic reactions and to the right for endothermic ones, affecting the concentrations of reactants and products accordingly. Understanding this helps us predict how temperature changes influence chemical systems, which ties into the overall theme of how conditions impact reaction dynamics. When we add an inert gas like argon to a reaction system, but keep the volume constant, the overall equilibrium typically remains unchanged. That's because inert gases don't participate in the reaction, they're just there in the background. So, adding them doesn't alter the partial pressures or molar concentrations of the reactants and products involved. The key point here is that the equilibrium state depends on the partial pressures of the reacting substances. Since inert gases don't affect these, the equilibrium remains undisturbed. However, it's important to remember that if the inert gas were to be added at constant pressure, or if it were a reactant or product involved in the reaction, then the reaction quotient could change, and the equilibrium could shift. This concept ties back to our overall theme, understanding what factors influence equilibrium, and when those factors cause a shift versus when they don't. A catalyst works by increasing the rate of a chemical reaction, and it does this by providing a new pathway that requires less energy for the reaction to proceed. Think of it like opening a shortcut that makes it easier for reactants to turn into products. This new pathway lowers the activation energy for both the forward and reverse reactions. Importantly, because it lowers the activation energy for both directions equally, it speeds up how fast the reaction reaches equilibrium, but it doesn't change the position of that equilibrium. So, the amounts of reactants and products at equilibrium remain the same. Another key point is that catalysts are not included in the balanced chemical equation, nor do they appear in the expression for the equilibrium constant. They're just there to help the reaction get there faster. And finally, if a reaction has an extremely small equilibrium constant, meaning it hardly proceeds to form products, then adding a catalyst won't really help much. It's all about making the path easier, but it can't do much if the reaction is already strongly unfavorable. Let's talk about the dielectric constant, which essentially describes how well a polar solvent like water can dissociate into ions. It's a measure of the solvent's relative permeability, meaning how easily it allows ions to separate and move around. When water causes ions to split apart, we call that process ionization or dissociation. Once the ions are separated, they become surrounded by water molecules, a process known as hydration. Now, organic acids such as acetic acid and formic acid are interesting because they don't fully ionize in water. Instead, they only partially ionize, typically less than 5%. This partial ionization affects how these acids behave and interact in solutions. Moving on to neutralization reactions, this is where an acid reacts with a base to produce a salt and water. It's a fundamental concept because it explains how acids and bases neutralize each other, leading to the formation of salts, which are important in many chemical and biological processes. Understanding these concepts helps us see how acids, bases, and salts interact, and how their behaviors are governed by properties like the dielectric constant and ionization capabilities. This knowledge ties directly into the broader theme of chemical interactions and solution chemistry. Now, when water interacts with hydrogen ions, it actually forms hydronium ions, which have a trigonal bipyramidal shape. This means the water molecule bonds with the hydrogen ion, resulting in H3O+. It's a key concept because it illustrates how acids behave in water. For example, we can write the reaction as HX breaking into H+ and X-, or more specifically, when HX reacts with water, it forms H3O+ and X-. According to Arrhenius theory, acids are substances that dissociate in water to produce H+ ions, whereas bases are substances that produce hydroxide ions, O-, in water. This idea helps us understand how acids and bases behave in aqueous solutions. So to sum up, acids release H+ ions, which can associate with water to form hydronium, and bases release O-ions. This concept forms a fundamental part of our understanding of acids and bases in chemistry. According to Brønsted-Lowry theory, an acid is a substance that can donate a hydrogen ion. Conversely, bases are substances that are capable of accepting hydrogen ions. In simple terms, acids are proton donors, and bases are proton acceptors. This concept helps us understand how acids and bases interact in various chemical reactions. It's a fundamental idea that connects to the overall theme of how substances behave and influence each other in chemistry. Recognizing these roles clarifies many types of chemical processes and reactions we encounter. According to Lewis, acids are defined as species that accept an electron pair, while bases are species that donate an electron pair. This concept shifts the focus from protons to electron pairs. It's important to note that in Lewis theory, acids do not need to have a proton at all. Instead, they are characterized by their ability to accept electron pairs. For example, BF3 doesn't have any protons, yet it still acts as an acid by accepting a lone pair of electrons from a base like NH3. When BF3 reacts with NH3, it forms a coordinate bond by accepting the lone pair. This highlights how Lewis acids and bases operate based on electron pairs rather than protons, broadening our understanding of chemical reactivity within the overall framework of acid-base interactions. Always, the stronger acid donates a proton to the stronger base. This is a fundamental rule in acid-base chemistry. Strong acids, like perchloric acid, hydriodic acid, and nitric acid, dissociate very easily in water. Because of this, they form weak conjugate bases. Think of it this way: the stronger the acid, the weaker its conjugate base. Conversely, weak acids tend to have very strong conjugate bases. For example, hydrofluoric acid and acetic acid are weak acids, but their conjugate bases are quite strong. This relationship is key to understanding how acids and bases behave in different situations, especially in aqueous solutions. It ties directly into the overall theme of ionization, showing us how the strength of acids and bases influences the strength of their conjugates and the direction of proton transfer. Let's explore how we can distinguish between acidic, basic, and neutral solutions based on the concentrations of hydrogen ions, H+, and hydroxide ions, O. When we talk about water, we often omit its concentration from the denominator in calculations because pure water's concentration remains constant. Instead, water's role is incorporated into a constant called the ionic product of water, or Kw. This allows us to focus on the variability of H+ and O in different solutions. Now, the dissociation of water can be represented by a simple equilibrium equation. What's interesting is that in pure water, one water molecule donates a proton, acting as an acid, while another water molecule accepts that proton, acting as a base. This simultaneous process results in a dynamic equilibrium that defines pure water's neutrality. This equilibrium is key to understanding the ionization constant of water and the ionic product, Kw. It forms the foundation for understanding pH and the behavior of solutions. Recognizing this balance helps us see how solutions shift toward acidity or alkalinity depending on the relative concentrations of H+ and O. Let's start with understanding how to calculate pH. The formula is pH equals negative log of the hydrogen ion concentration. Written as pH equals log H plus, this helps us quantify acidity or alkalinity in a solution. Next, we move on to substituting the equilibrium concentrations into the equilibrium constant equation for the primary reaction. By doing this, we can solve for the degree of ionization, which we denote as alpha or alpha. To do that, we first determine the equilibrium concentrations of each species involved. Then, we convert the changes in concentrations into expressions in terms of alpha, which indicates how much dissociation or ionization has occurred. It's also important to list the initial concentrations of each species involved in the primary reaction in a tabular form. This makes it easier to keep track of how concentrations change during the reaction. Now, we need to consider possible reactions involving a species that can act both as an acid and a base. These are called amphiprotic species. For such reactions, we write balanced equations for each possible pathway. Among these reactions, the one with the higher ionization constant, or Ca, is identified as the primary reaction. The other with a lower Ca is considered a subsidiary reaction. Before dissociation, the species present are identified as Brønsted-Lowry acids or bases. This classification helps us understand their behavior in proton transfer reactions. To evaluate the pH of weak electrolytes, we follow some steps. Remember, the pH scale, which measures hydrogen ion concentration, has been extended to include other species and quantities, broadening its application. At a given temperature, T, the value of Ca serves as a measure of an acid's strength. The larger the Ca, the stronger the acid. The Ca value is dimensionless and is typically considered for concentrations of 1 molar for standardization. The general dissociation formula for weak acids is straightforward. The acid HX dissociates into H+ and X- ions. The dissociation or ionization constant, Ca, quantifies this process and is a key parameter in understanding acid strength. Finally, understanding the ionization constants of weak acids allows us to predict how much an acid will dissociate in solution, which directly impacts the pH and overall chemical behavior of the solution. Their conjugate bases are weak bases. This means that when an acid donates a proton, the resulting conjugate base doesn't readily accept protons again. Their conjugate bases are quite weak, which indicates that the original acid was strong enough to dissociate more completely. When we talk about weak acids, they only dissociate partially in water, meaning only a small portion of the acid molecules actually release their protons. In contrast, strong acids are completely dissociated in water, so all of their molecules break apart into ions. Understanding these differences in acid and base strength helps us predict how substances will behave in solution and is fundamental to grasping chemical reactions in aqueous environments. Let's take a closer look at this reaction. HCl in aqueous solution reacts with water to produce H3O+ ions and chloride ions. Now, an important point here is that water is actually a much stronger base than the chloride ion. Because of this, the equilibrium essentially shifts far to the right, meaning the reaction goes almost completely in that direction. We don't usually measure a specific equilibrium constant in this case because it's so large, much greater than 1. This highlights a key concept in acid-base chemistry. Whenever a reaction involves an acid and a base, the equilibrium tends to favor the formation of the product where the proton ends up with the stronger base. So, in this case, water, a stronger base, accepts the proton from HCl, leading to the formation of hydronium ions. Understanding these tendencies helps us predict how acids and bases behave in different environments, which is fundamental to grasping the overall theme of acid-base strength and reactivity. Now, let's talk about the equilibrium constant for base ionization, which we call the base ionization constant, or Kb for short. This constant essentially measures how much a base ionizes in solution. If we denote the initial concentration of the base as C and the degree of ionization, that is, how much the base actually ionizes, as alpha, then we can express the equilibrium constant in terms of these parameters. This helps us understand the extent to which the base undergoes ionization at equilibrium. Connecting this to the overall theme, it's important because it gives us a quantitative way to compare different bases and their strengths. The larger the Kb, the stronger the base, meaning it ionizes more readily. So, understanding Kb and how it relates to concentration and ionization degree helps us predict the behavior of weak bases in solution. When dealing with a conjugate acid-base pair, it's important to understand how their equilibrium constants relate. If we consider a net reaction formed by adding 2 or more reactions, the overall equilibrium constant is actually the product of the individual constants for each reaction. This means that the combined effect of multiple steps can be understood by multiplying their constants together. Now, connecting this to our broader theme, it highlights how acids and bases are interconnected through their equilibrium behaviors. Specifically, the relation between Ca and Kb is fundamental. Ca measures the strength of an acid, while Kb measures the strength of its conjugate base. These two constants are mathematically linked, and understanding this relationship helps us predict how acids and bases will behave in different environments. So, in essence, grasping how these constants relate not only deepens our understanding of acid-base chemistry, but also provides a powerful tool for predicting reactions and their extents. Some acids, such as oxalic acid, sulfuric acid, and phosphoric acid, have more than one ionizable proton per molecule. These are known as polybasic or polyprotic acids. The key idea here is that these acids can release multiple protons during ionization. For example, dibasic acids have more than 2 ionizable protons, while tribasic acids have more than 3. Now, an important point to remember is that higher-order ionization constants are actually smaller than the lower-order ones. What does that mean? It means that as you remove successive protons, it becomes increasingly difficult. This difficulty arises because removing a positively charged proton from a negatively charged ion involves overcoming electrostatic forces. So, in essence, the more protons an acid can release, the harder it becomes to remove each additional proton, especially the higher up in the chain. This concept is crucial for understanding the behavior of polybasic acids and their ionization characteristics, which ties back to the overall theme of acid strength and reactivity. Let's start by noting that sulfuric acid, H2SO4, is a stronger acid than the hydrogen sulfate ion, HSO4-. When the first hydrogen is removed from H2SO4, it becomes HSO4-, and removing that first hydrogen actually makes it harder to remove the second one. This highlights an important concept. The extent of dissociation of an acid depends largely on the strength and polarity of the H, a bond. As the energy required to break the H, a bond decreases, the bond becomes weaker, and the acid becomes stronger. Think of it this way. If the bond is weaker, it's easier for the hydrogen to leave, making the acid more potent. Another point to keep in mind is that as the size of the group increases down a group in the periodic table, the H, a bond strength decreases, which in turn increases the acid strength. Similarly, if the electronegativity of A increases, the acid strength also increases because it stabilizes the negative charge after dissociation. Now, moving on to polyprotic acids, these are acids that can donate more than one proton or ionizable hydrogen. They tend to ionize in steps, meaning each hydrogen is removed sequentially. Interestingly, the ionizable hydrogens in these acids can have different acid strengths, or sometimes they can be equivalent. For example, HCl is monoprotic, meaning it has only one ionizable hydrogen, while H2SO4 is diprotic, with 2, and H3PO4 is triprotic, with 3. The key point here is that in polyprotic acids, each hydrogen is removed one after the other, which affects how the acid behaves in solution. Most importantly, many acid molecules contain more than one ionizable hydrogen, which is why understanding polyprotic acids is so essential to grasping overall acid behavior and strength. So, in summary, these concepts about bond strength, electronegativity, and the stepwise ionization process are all interconnected and help explain why different acids behave the way they do in various chemical environments. Let's take a look at how bases tend to behave differently from acids. Unlike acids, where strength often depends on how easily they can donate protons, bases show an opposite trend. For example, in terms of the H3O+, water, and O-, the acidity decreases in that order. Similarly, for ammonium and its related species, NH4+ is a stronger acid than NH3, which in turn is stronger than NH2-. This pattern highlights that cations generally tend to be stronger acids than neutral molecules, and neutral acids are stronger than their corresponding anions. When we compare oxyacids, like H2SO4 and H2SO3, the one with more oxygen atoms, H2SO4 tends to be the stronger acid. The same goes for nitric acid compared to nitrous acid. HNO3 is stronger than HNO2. This brings us to an important point about oxidation numbers. The higher the oxidation number of an element in an oxyacid, the stronger the acid tends to be. And as a related concept, the stronger the acid at donating H+, the weaker its conjugate base will be at accepting H+. Understanding these trends helps us predict the relative strengths of different acids and bases, which is crucial for many chemical reactions and processes. Now, let's talk about the common ion effect, which involves reducing the concentration of hydrogen ions. Essentially, this effect occurs when we add a substance that introduces an ion already present in the dissociation equilibrium. This causes a shift in the equilibrium position, according to Le Chatelier's principle. So, in simple terms, if you increase the concentration of one of the ions involved, the system responds by shifting to counteract that change. This is a key concept because it explains how adding certain ions can suppress or enhance the dissociation of acids and bases. It's an important aspect to understand when we're analyzing solutions and their pH behavior, tying back to the overall theme of how equilibria respond to changes in their environment. Let's start by discussing the degree of hydrolysis. We can say that it is independent of the concentration of the solution, which means that changing how much salt or solution we have doesn't affect how much hydrolysis occurs. Instead, the pH of these solutions is primarily determined by their pK values, which are specific to each acid or base involved. Now, if the difference between the pH and the pK is positive, the pH of the solution can be greater than 7, indicating a basic environment. Conversely, if that difference is negative, the pH will be less than 7, making the solution acidic. Moving on, salts are formed through reactions between acids and bases in definite proportions. Once formed, these salts undergo ionization when they are dissolved in water. This process produces cations and anions, which can either exist as hydrated ions, meaning they are surrounded by water molecules, or they can interact with water to reform the original acids or bases. This interaction between water and the ions of the salt is what we call hydrolysis. It's a key process because it influences the pH of the solution, depending on how these ions behave in water. Understanding hydrolysis helps us grasp how salts affect solution acidity or alkalinity, which ties back into the broader theme of acid-base chemistry and solution behavior. Now, let's talk about buffer solutions. These are solutions that resist changes in pH when you dilute them or add small amounts of acid or alkali. Essentially, their main feature is their ability to maintain a stable pH under different conditions. This stability is crucial in many chemical and biological processes. Buffer solutions are prepared based on our understanding of pKa and pKb values for acids and bases. By knowing these values, we can control the ratio of salt to acid or salt to base to set the desired pH. This is a key concept because it allows us to design buffers tailored to specific applications. Overall, buffer solutions play a vital role in maintaining the pH stability necessary for proper functioning in various systems, and understanding their preparation and properties helps us better manage chemical reactions and biological functions. As a general rule, for a salt to be able to dissolve in a particular solvent, its solvation enthalpy must be greater than its lattice enthalpy. This means that the energy released during solvation needs to overcome the energy required to break apart the solid lattice structure of the salt. It's also important to remember that the solubility of salts depends on temperature. As temperature changes, so does the balance between these enthalpies, affecting how much salt can dissolve. Now, the amount of solvation enthalpy depends largely on the nature of the solvent itself. In nonpolar solvents, for example, the solvation enthalpy is quite small. Since it's not enough to overcome the lattice enthalpy, salts tend not to dissolve in nonpolar solvents at all. So, when we talk about the solubility of salts, we're really considering two key factors: the lattice enthalpy of the salt and the solvation enthalpy of its ions in the solution. To dissolve, the attractive forces holding the ions together in the solid must be overcome by the interactions between the ions and the solvent molecules. And the process of solvation itself is exothermic, meaning it releases energy. This is why we say the solvation enthalpy is always negative. It's an energy release during the process of the ions interacting with the solvent. Understanding these concepts helps us see why some salts dissolve readily, while others are sparingly soluble, depending on the interplay of these enthalpies and conditions. Let's take a closer look at the term KSB in the context of our previous discussions. KSB, or the solubility product constant, can actually be expressed as QSB when the concentrations of the ions in solution are not at equilibrium. So in that case, KSB equals QSB. However, when the solution is at equilibrium, KSB helps us understand the direction in which the process will proceed, whether the salt will tend to precipitate or dissolve. Now imagine a solid salt with a specific formula, say, for example, sodium chloride, and its molar solubility, which we denote as S, is at equilibrium with its saturated solution. The key point here is that the solubility product constant, KSB, is a measure of how much salt can dissolve before the solution becomes saturated. This concept is central to our overall theme because it helps us predict and control processes like crystallization, precipitation, and dissolution, which are fundamental in many chemical and industrial applications. Understanding KSB and QSB gives us valuable insights into the behavior of salts in solution, guiding us in both research and practical scenarios. Let's talk about protonation. Protonation is essentially the process of adding a proton, which is a hydrogen ion or H+, to an atom, molecule, or ion. When this happens, it forms what's called the conjugate acid. This process is quite fundamental in chemistry because it influences how acids and bases behave. Now, moving on to the effect of ion concentration on salt solubility. If we increase the concentration of one of the ions involved, that ion will tend to combine with its opposite charge partner. As a result, some of the salt will start to precipitate out of solution again. Conversely, if we decrease the concentration of one ion, more salt will dissolve to restore the balance, increasing the concentration of both ions until equilibrium is reestablished. This brings us to an interesting point about weak acids, like phosphates. Their salt solubility actually increases at lower pH levels. Why? Because at lower pH, a lot of the anions get protonated. That is, they gain protons, which reduces their charge. With fewer free anions, the salt becomes more soluble because there's less ionic interaction holding it together. Connecting this to the overall theme, understanding how protonation and ion concentrations influence solubility is key in controlling reactions and processes in chemistry, especially in biological systems and industrial applications.